Hello everybody, welcome to tutorial 1. It's the second tutorial of this week. I hope you've been having an excellent week. This week, instead of going over a bunch of syntax and stuff, we're actually going to get to dive in with 3 different examples about the core concepts of week 2. So the first one is an induction on SUM2, the second one is an analysis of a program called SUMCubes, and the third one is a construction of the natural numbers in Racket. So the first one, induction on SUM2, is that we've been looking at a lot of closed forms recently in lecture, and one of them that appears is this. The sum of the natural numbers from 1 to n is n times n plus 1 over 2. And this is kind of a curious result, and it's not proved in lecture, so we're going to prove it now using a technique called induction. If you're unfamiliar with induction, I'll give a quick explanation. The idea is that you have a base case, so if I want to prove a statement about all the natural numbers, something that holds from 0 to as high as I want, I can prove it for 0 or 1, and then I also prove that if it works for a number m, it'll also work for m plus 1. And this is kind of like if you were trying to program a robot to climb ladders, how instead of teaching it to climb a ladder with 11 rungs and a ladder with 12 rungs and so on, and keep programming it in at each of those different rung ladder heights, you would instead program it how to get on a ladder and how to climb up one rung. And then the robot could just get on the ladder and repeat its going up one rung until it reaches the top of the ladder. So I'm going to switch to a whiteboard right now and do that proof by induction for you guys to see.
Welcome to the induction portion of the video. Here I'm going to prove the following result, that 1 plus 2 plus all the way up to n is equal to n times n plus 1 over 2. And I'm going to accomplish this by induction. So the reason that you're seeing this here in computer science and not in your math courses, well, you'll also see it in your math courses, is because induction is very similar to recursion. So with recursion, we had our trivial case and then our reduction step. And with induction, we're going to have our trivial case or base case and then an induction step. So for our trivial case, we're going to look at n equals 1. So if n equals 1, then the sum 2 of n is just 1 itself. 1 plus up to n is just 1. And then our formula on the other side is 1 times 1 plus 1 over 2, which is 1. And since 1 equals 1, we have a good base case. So what I've done in this base case is just verified that my formula holds. I've shown that this result holds for n equals 1. And then I'm going to say now, assume that 1 plus 2 all the way up to m equals m times n plus 1 over 2, assume that that result holds for some m. And if you can't see, there's just a little 2 under there. And now I'm going to say, what happens when n equals n plus 1? Well, what's interesting here, I'll put this back up to height, is that I have the sum 2 up to n plus 1, and I'm just going to rewrite that, rebracket that a little bit. Put an m there, m plus 1, it's the exact same sum, and then I'm going to use this thing that I assumed down here. I'm going to replace that whole 1 up to m with m times n plus 1 over 2 plus n plus 1, and then I'm going to factor out m plus 1 over 2, so then I get m plus 1 over 2 times, factoring out of this first part gives us m, factoring m plus 1 over 2 out of m plus 1 gives us 2, but now you'll see that this is just our formula applied to n plus 1. It's this formula with n equals n plus 1. So what's really crazy here is now that we get to use the magic of induction. So since we've proved it for n, and if we also proved that if it works for m, then it works for m plus 1. So what this means is that since the formula holds for 1, we can just use 1 as our m, and we know that the formula holds for 2. But then we can use 2 as our m and learn that it holds for 3, and then now we know that our formula holds for any natural n. So there's a proof by induction. I hope you enjoyed it, and I hope that you see how it relates to recursion, with the trivial case in recursion being analogous to our base case right here, and the reducing case, the reduction case in recursion, being analogous to our induction step.
Okay, so our second example here is sum cubes. And it's kind of like sum 2, except instead of taking 1 plus 2 up to n, you take 1 cubed plus 2 cubed up to n cubed. So we're going to do a little bit of the analysis, the kind of analysis that we've been seeing in the earlier part of this week. So I've written it out here. We've got our familiar sum 2 powered by our Taylor recursive sum between that we developed earlier. And now I've written out sum cubes of here. So it takes in an input, it's expecting an integer. If it's 0, then we're going to return 0 as our base case. I could have had my base case as 1 or my trivial case as 1 equals n1 and done it there, but thinking about the next example we're going to do with the natural numbers, it seemed a better fit to start with 0. So if we have 0, then we're going to give back 0. Otherwise, I'm going to return the sum of the number we got cubed and some cube of 1 less than that. So I'll show you a couple examples right now of how this works. Sum cubes 0, 0, sum cubes 1, sum cubes 2 should give us 9, and sum cubes 3, 36. Sum cubes 4 should give us 100, right? Because we're going to add 64 to 36. And now that we know that this whole thing works, I'm just going to throw in sum cubes 0 and pull up the stepper. So hopefully this formats in a way that we can see. I'm going to pull the stepper window out. And here's our first step. Function substitution, of course. We have our trivial case, and then we can output 0. So 3 steps. If we crank it up to 1, we won't be in our trivial case. I'm going to pull out the stepper again. And so we do our function substitution. You can see that we've moved up to 9 steps here. So that's 6 more than our previous one. False. We will do the addition of 1 cubed and then sum cubes of 0. Oh, this sub1 function right here is just like add 1 from lecture, but it subtracts 1 instead of adding. I know that hasn't been formally introduced yet. And then here, function substitution. So we've already gone through 5 steps, 5 extra steps. And then we have this whole sum cube 0. So we're going to do the 3 steps that we've already done, 1, 2, 3. And then we get this extra sixth step, which is actually the 9th step at the end. And then it's the addition is the bonus step. So I'm just going to do 1 or 2 more so as to explain the concept but not bore you by going all the way up to 6 million steps. So you see we have 15 steps, which is 6 more than last time. So it seems that we're adding 6 every time. And I'll step through false, exponentiate, step through false, exponentiate, step through true, add it all up and get up to 9. So now if we look back over here in the slides, I've tabulated the results for 0 to 3. So as you can see, the steps are going up by 6 each time, and we start with 3. So can we find a closed form for the number of steps? Yes, we can definitely find a closed form. And if your solutions in assignment 2 are timing out, you might want to think about looking for a closed form, especially for some of the recursions or some of the examples where a closed form can easily be found. Some of them are not so easy to detect. But this one, as we've said, we're going to add 6 each time, and we start with 3. So in infix notation for the addition here, we have some cube steps of n is 3 plus 6n. And also, you might have noticed that every result, that is a perfect square right here. And I've also added sum to n I've augmented our table with sum2n. And if you just stare at this for a second, you'll see that there's a glaring correspondence, is that sum cubes of n is the square of sum 2 of m. And this is actually pretty interesting, and it holds for all n. So I've left that as an exercise at the end of this video for you guys to do, is to prove that using the induction method. So our third example is the natural numbers. And you say, wait, I already got the natural numbers down. That's just 0, 1, 2, 3, 4, and you keep going. But that definition has a few problems. One, it's not rigorous in the sense that you can tell a computer, because it's an infinite definition. It is rigorous in a mathematical sense. You just say the natural numbers are the natural numbers. But we have an even more rigorous definition via the Peano axioms that completely characterizes the natural numbers. But for our purposes, and for this example, we don't want to use either of these definitions, this one being too simple to be explicable in a finite way, this one being too complex to work with in our Racket programming environment. So if you look in the 2015 lecture summaries, you can find this example. I've modified it a little for these slides. It's more rigorous than the first definition and easier to work with the second. You just need to take these properties and put them together, and then you get the natural numbers. So 1, z is a natural number. 2, there's a successor function s, which maps a natural number to the next natural number. And 3, for every natural number n, s of n is a natural number. So if you just take these 3 properties, you get the natural numbers. And here are some remarks, some ways of understanding this definition, because it's still kind of technical. Not as technical as the second definition with the Peano axioms, but much more technical than just saying the natural numbers are 0, 1, 2, and so on. So z is our 0. S is kind of like add 1. That's when I say succession operator, I mean go to the next natural number, add 1. So 1 is s applied to z, so that's 0 plus 1, and 3 is 0 plus 1 plus 1 plus 1. So for the programming outcomes of the last example, we're going to want to put this in Racket. So what I'm going to do is use our new define struct to build our succession operator. I'm going to give a predicate. I'm going to try to see if we can convert to and from our Racket built-in and our new natural numbers, and also see if we can do some computation. So here we go. And you're saying, why do this other than as an exercise? Well, one day you might want to move past Racket's built-in arithmetic. And when you want to, for example, one that's coming up is in exact numbers. They say, why don't we have square roots? Well, if you just use Racket's built-in numbers, there's not really anything you can do about that. But if you want to build your own numbers, one day you could put in the functionality of square roots. So here we go. I've just defined S as the empty set. This little tick and then parentheses represents the empty set in Racket. And this define struct S of next is, of course, the define struct with one field. So this will give us a predicate, a field selector, and a constructor function that we can use. So I can write just some constants in, define 0 to be z, define 1 to be make s. So this is s applied to z. Define 2 as make s of z. And then finally, I'm going to say define 3 to be make s of 2. And you can notice that I'm using my own defined 2 and not Racket's built-in number 2. The first programming goal we had was to have a predicate. So why not call them natural numbers, not natural numbers, natural numbers, nat of n. And there's a few things I need to check. And the first one is that I need to check, I'm going to do this recursively, of course, to practice recursion. If the argument of the function is empty, then we can say true because it's z. Otherwise, we want to make sure that it is an s we want to make sure that our natural number is an S, so we're using our predicate from this struct, and we also want to make sure that what's inside of it, S next, using our field selector, is also a natural. So what this is going to do for us is that we're going to be able to see, even if I try to trick us by doing something like make, not a natural number, make S of 2, and I call this 3, because this is kind of like a counterfeit 3. I'm going to say this is 2 and add 1, right? That's a 3. But hopefully, if I've programmed my predicate correctly, if I say natha of 3, I will get an infinite result. So I did a user break. Since Racket didn't output immediately, I suspect that something is off. Aha. I don't know why I programmed it like this, but I need to do natha s next of n. It's interesting because when I wrote that, I wrote it in the correct order and then went back outside of the brackets to put in that s next call. So natha of nan, we'll try this one out, gives us false, and natha of 3 should give us true. Now I'm going to write some conversion functions, but I'm actually going to only write one and give the other one to you as an exercise. It's a little gift from me to you. So I'm going to convert num arrow nat, and I'm going to use the convention of calling Racket's built-ins nums. So num arrow nat of n. I'm actually going to just think ahead about this a little bit and make a helper function called num nat help of n and an accumulator. And then in this one, I'm just going to use it as a little wrapper called numnat help, not a true wrapper because it's doing something non-trivial, numnat help of n and the empty set. And what I'm going to do here, how I'm going to do it, is when Racket gives me a natural number, I'm going to start with a 0 in my definition and say a 7 that someone gives me to convert. And then I'm going to go to a 6 and a 1, and then a 5 and a 2, and keep changing them until this one hits 0, till the num that they give me is 0, and then I'll know that I have made enough structs. I have done make s to empty as many times as I've needed. So why don't I go ahead and write that? If 0 ha n, and 0 ha does what you think it would. If it sees Racket 0, then it evaluates to true, and otherwise it evaluates to false. I'm going to give back my accumulator. That's the number that I'm making. Otherwise, I'm going to call numnat help on sub 1 of n and make s of ac. So here you go. I'm subtracting 1 from n and I'm making s to ac. And now I've got my little recursive definition. And let's see if we can give this a little test to see if I haven't made any more mistakes. Num nat 6, and I should get 6 make s's and a z. So there's my z, the empty set, matches my z definition up here. 1, 2, 3, 4, 5, 6. So that bodes well. Now the last thing I'm going to do is define some arithmetic, because these aren't really numbers in the sense that we want unless we can do arithmetic. Like anyone can give you an ordered list. Like if I give you, apple, bear, car, duck, that's an ordered list too. And you could say, well, why aren't those my natural numbers? Well, we have a familiar arithmetic that we would like to employ. So I'm going to say define plus of n1 and n2 for nat1 and nat2 to be, I'm going to just use the exact same strategy. Actually, I'm not going to use the exact same strategy. I'm going to say if empty ha of n1, a very similar strategy. If n1 is 0, then I can just return n2, right? That's a very easy addition to do, adding 0 to something. And otherwise, I'm going to call plus s next. Now you can see that I'm assuming that these are both nats, because otherwise I won't be able to call s next on it. So if you wanted to put this in practice, like on a website or something, you would have to defensively program it and use the NatHum before you pass them through here, or else you might get an error. Somebody's going to hack you. That's not going to be very fun. So make s of n2. Now let me try to test my addition. I'm going to say plus 3 and 2, and I have 5 make s's and an empty. So the very last one I'm going to do is multiplication, and thinking about it a bit, I think I'm going to need some help from a helper function. So I'm going to say define times n1, n2, mult for multiply of n1, n2, and an accumulator, I'll use empty. So this is like putting in 0 in my sum between at the end. You know how we used sum between for sum2 and you put a 0 in? This empty, since empty is the same thing as z, which is our representation of 0, acts as our 0, mult of n1, n2, and an accumulator if n1 is 0, which is empty in our representation, n1, then I can give back our accumulator. So if I multiply by 0, I'll get 0. And otherwise, I can call mult of s next n1, n2 again, and then plus, I'm going to use my function, n2 and act. So this multiplication is very simple, very basic. It works by repeated addition. So if I take 3 times 4, I'm going to add 4, 4, and 4 to get 12. So why don't I try that out? I can write, after racket loads, times num arrow nat 4, and well, let's live on the wild side and go big. Num arrow nat 6. So hopefully, but of course, I did not put in that symbol. And I also hit run instead of enter. So that looks to me like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 make s applications indeed. So we have successfully multiplied, which is the goal. We have made our natural numbers. So my challenge to you, if you accept it, is to extend this to the integers, and then one day you may get algebraic numbers and be able to do all the computations with square roots, with radicals that your heart desires. So here are the practice problems. Thanks so much for watching. Remember to like, comment, and subscribe. Oh wait, that's something else. That's not this video watching platform. That's another famous video watching platform. Have a great week. Thanks for watching.